So as I've been working on this series of projects here around a 65265, trying to get to, my next iteration of a single board computer using a 265, I've marked a couple of items at the bottom of my main blog post here about unresolved items. One of those is a parallel interface bus, and I recently made it through all that. I have this parallel interface bus working, and so I think I'm good on that. I'm going to kind of check that off. I have a separate post just on the parallel interface bus. But then another issue that I had, and I could not resolve at the time, was these shadow vectors. And so I've started another blog post just to capture some information around that in case anybody wants to set this up and is looking for something that maybe walks through it in a little bit more detail. So here's the board that I'm using. This is the SXB from Western Design Center. So it's their 265 with USB serial interface, static RAM, and external flash capability. And when I first started working with this back in December, I wanted to do something simple like have a button that I can push that would bring a signal low on one of these pins. And then I could have an interrupt service routine that then processes and does something. For example, maybe turn on an LED over here. But I could not get that to work. And, I went over to the sample code. There's a few, maybe 4 sample projects that come with Western Design Center tools. So I grabbed the tools. It has the assembler that I'm using. And at the bottom of those samples, it has this block of code. There are vectors, basically pointers, so that when certain interrupts happen, the processor goes to a certain address, looks for essentially a pointer that says you're going to point to some procedure. For example, if I have an interrupt, this IRQ break, it's going to look at FFFE and whatever you're pointing to. In this case, this procedure, this routine called IRQ handler, it's going to then jump to it, and basically that's your interrupt service routine. Or if I do a reset, it's going to jump to whatever's labeled start. And these are the vectors that we would use for that. Now, those don't actually work, though, on this because, at least not for my own user interrupts, because if I look at the memory map on this, those addresses are right here in this FF space, FF00 through FFFF, and this is labeled on-chip interrupt vectors. And that's on the chip itself. So this is part of the 265. It's hard-coded as part of the hardware. So there's got to be a way to say, well, I want to replace those. I don't want to use those vectors. I want my own custom interrupt service routine for some one or more of the different types of interrupts that I can set up on the system. Well, that presents a challenge, and I know that this sample block here, that's not going to work. But then in the sample code, there's also this shadow vectors, and it's at an address down at 7E something. And if I look at 7E, that happens to be within my cache memory. That's the external static RAM. So to me, that kind of led me to believe that I could just simply place my pointers, my vectors, within the appropriate address within this space, and the system would use those. Why else would there be this block of stuff here that says it starts at 7E0, and then I have all of these different pointers that I could fill in? I could not get that to work. And that's even labeled in the code shadow vectors. And if I go search the data sheet, there's no mention of the word shadow, and this concept of shadow vectors really isn't documented as I go out and look around. Of course, I use some of the AI tools, and they give me information that may or may not be helpful. Ultimately, I was not able to get this figured out, though, at that time, back in December. Well, I've kind of come back and revisited it, and I made a post real quick over to 6502.org, and Andy recently had just mentioned, responded to me and said, hey, maybe go check out the source code for the built-in ROM that's on this 265. Now, I've done that a couple of times. I've worked my way through that code a couple of times, trying to understand it. But there was definitely something I didn't catch the first however many times I've scanned through that I kind of caught this time as I went through it. And what I would come down and point to is a couple of blocks in this post that there is a ROM initialization file and some RAM file. But if I look at the ROM initialization, there's some code that here caught my eye that basically it's looking at a range of maybe interrupt vectors that are in the code, and it's copying them down to an address UBRK. And if I go look that up in this other file, that's way down here at 100. So 0, 100. And this is listed as mensch vectors and buffers at 100 hex. And I look through that list and it's like, oh, this looks really good because there's my IRQ vector I want to be able to have my own interrupt service routine for. And one of the other ones I was working with was a negative edge on pin 4 of port 6. And that would be an edge IRQ. So I see, oh, there's something there for that too. So as I looked into this, and maybe the tip from Andy was, well, there's something there that already does this. So, okay, let's go look at that. And so I set aside anything that was up in the FF range or anything that was up in the upper 7,000 range. And just looking at this, well, what if can I modify what's at the 100 range and replace whatever these are pointing to my own interrupt service routine? So could I take the IRQ and point to my routine? Can I go to the back down to the edge interrupts and point to my own routine for that? So that's what I got in and did. And I initially, it's not just a pointer you put in there. You have to also say to do a jump. So I put in code that looks like this that basically says, okay, and maybe I'll go back to one of these up here. So 100 is where this started. And if I get down and I reserve 4 bytes for break and 4 bytes for NMI, so that was 100, 104, 108 is where this user, this is IRQB basically, starts at that location. So I came down here and said, well, at that location, 108, store 4C, which is the opcode for a jump. And then at 109, I store, and at 110 or 10A, I basically then store the other part, but these two are storing the 2 bytes of an address that is a pointer to my interrupt service routine, which I called IRQ handler _ IRQB. I then did the same thing for this negative edge 64 interrupt. Again, I can come back up to this list. I can count down to where that edge interrupts pointer is. And that location is then what I wrote to. I said, write the jump opcode, then write out the lower byte and upper byte of this address to 119 and 11A. So 11.9, 11A. And here what we'd have then is that the less than is saying take the lower byte of what was or is the address of this routine I have, and then take the upper byte, store those 2 bytes in 119 and 11A. So I'm going to store a jump and then point to my interrupt service routine. And that worked. So at that point, success. So I put in a little bit of code, and I just thought I'd real quick show this to supplement what's on this blog post, and I'll put the link. I'll embed the link to the YouTube video here at the bottom of this. I also have a link here to the code that I'll use in this demo here that I show real quickly. There is also this page in the manual for the ROM monitor, and it does list out these same things, so you don't have to go track down the source code. But this was labeled internal RAM locations used by library subroutines for data transfer. That wasn't enough for me to latch on and say, oh, this is where I would write my pointers to. Now, coming back in hindsight, it's like, okay, that's helpful now that I have a little more context to this. And I had tried that way back when. So in addition to trying, the stuff in the upper 7,000 range, I had tried this one down here, all edge IRQs. But there's another thing I found is that you also have to, in addition to that, you have to have this user interrupt 108 implemented. You have to have a pointer to something for that. That one by itself works. Both of them together work. The other one by itself without something for the regular IRQB doesn't work. And so I'm going to assume there's some type of cascade that it goes through that generic IRQB or somehow is using that, or it's causing issues if it's not set up. That was there. And I do make a comment here. I'm sure I'm still missing details here. So some of you that look at what I've posted here, if you've got further things to clarify or if I'm misspeaking on any of this, do let me know, and I'll update this page with any additional information as I learn it. So I'm going to jump over to my code, and I started with the sample LED. There's a P72 LED sample that comes with the Western Design Center tools that basically turns on the LED, the P72 LED, which is a tiny little LED here that is connected to this CS2B line. And you probably can see it on this board. I've done some hacking and slashing a little bit. I had to cut some traces that went from the microcontroller to the external ROM upper addresses and rerouted some of those signals for use on a port, but not for use on the ROM. If you're interested in hearing about that, go back to my videos on the parallel interface bus, because those signals were causing issues with the parallel interface bus. So I had to split that out a little bit. But here I want to be able to use this board without an external flash. I just want to use the internal ROM. I want to use the static RAM. I want to turn it on. I want to upload a program to it, have it run that program. And I want to support interrupts in that program. So that's what I'm going to do here. And maybe what I'll do is I'll just start by loading up. I'll open up this Easy SXB that comes with the tools. And I'm going to go ahead and let's see, my board is plugged into USB with power, so I should be able to, let's see, connect to it. I don't think I have one of these running already. And I believe it's on COM4. Let me check that. Yep. Now I'm going to hit reset on the board just so you can see that it comes up with a Mensch monitor ROM or monitor that it's running here. And the way that this would work is I would say, okay, I want to go ahead and upload a program. I would go browse to my program and open that. And so that's taken the code that I assembled and it has uploaded into RAM at 2000 is where it uploads it. So I'm just going to tell this that I want to jump to 2000. And then it has now jumped to my code, which now should on this make it so that I can press a button and pull a line down. And I've got two lines that I can test. I have these two connections to two different inputs. This one right here, the purplish one, the purple one is connected to port 4, pin 1, so 41, P41, which is IRQB. So I'm just going to put this into the circuit so that that button does a pull down on that. The rest of what you see here is really just trying to debounce this button a little bit. But now I can come in here and I can press that button and that light will flash. So you notice it flashed twice. So when I press this button using the interrupt on IRQB, it flashes twice. Well, instead of that, I want to trigger a different interrupt, so I'm going to set this over to the side. This line is connected to port 6, and let's see, 7654. It's pin 4 of port 6, so it's 64. 64 happens to be one of the lines that supports a negative edge interrupt. So a falling edge on 64, I can tie an interrupt to. So I'm just going to interrupt it instead, and I'm going to go ahead and push the button. And you're going to notice it's going to flash 3 times. I have 2 different interrupt service routines. I just want to make sure I can trigger them independently. They're separate routines, depending on if this line goes low or this line goes low. So again, this one flashes 3 times. So that just allows me when I'm doing the test to make sure that it is running separate interrupt service routines. Now, code-wise, what's on my screen here, as I go down through this, there's a bunch of definitions. I trimmed a bunch out that were in the sample program, but there's a bunch of definitions in here to point to register for my edge interrupts, so I can enable those. There are flags, so I can detect which specific edge, was it P64 or something else that was interrupted essentially. My normal data direction for my ports and the actual port data registers the values that I want to put out on the ports or read in. But when I start this, I basically have the same initialization code that was already there. I then load up and store or write out to the port 6 data direction, and I say that the lowest bit is an output, and port 6 again is way over here, and that lowest port is what's going to the LED. So that's my LED driver. And then I write out 0, so turn the LED off if it happened to be on. Then I go to port 4, which is this one. That is a line that I can then trigger P41. I mark all of those pins as input. And then I put in comments that are all of the interrupt vectors and their addressing. So I know it starts at 100, and there's a user break, NMI, the user IRQ, that's at 108 hex, and I marked that as that's one I'm using here in this example. There's a few others I'm not using, and then I'm using this edge interrupt at 118 hex. I then have to go to those addresses and write in my pointers along with the jump code, and that's what these two blocks do. So I say go out to 108 and write in the jump opcode, followed by the 2 bytes that point to my IRQ handler underscore IRQB. And then I do the same thing at 118. I write the jump opcode and then a pointer to my NE64 interrupt handler. And then I basically go out to this interrupt enable, and I say enable IRQB, that's this highest bit. And then this one that you see here is to enable this negative edge on pin 64. So those are the 2 things that I'm going to turn on for edge style interrupts. And then I clear any interrupts if there are any already in the flag register. And then I then remove the restriction on global interrupts. So I basically say turn on global interrupts at this point with CLI. And then I get out of here. So when I first load this, coming from the Mensch monitor over here, it simply runs that and then gets out. And it goes back to the Mensch monitor and is just sitting there doing whatever it does when it's idle. But I, in the process, wrote these updated pointers to my interrupt service routines for those 2 things. So then when I do press the button and I pull one of those lines low, either the IRQ P41 line or the NE64 line, it's going to come down and run one of those 2 handlers. So I have the IRQB handler, and then I have the NE64 handler. And really all these do is toggle that LED with some delay in between. And so you can see I'm delaying roughly a quarter of a second or whatever. I put in 255, and then that calls this delay routine over here that basically with an 8 megahertz clock is about a quarter of a second. Now this is only a 3.68 megahertz clock, so it's obviously more than a quarter second, so it's maybe going on 2/3 of a second roughly. I don't have it dialed in real precise, but in that ballpark. And so that's these 2 routines. I come in, I say load up whatever is on ports, or load up a 1, write it out to port 6, basically turn on the LED, wait a little bit, turn off the LED, wait a little bit. I could have put these in loops, but I just was being maybe a little bit lazy here. Just turn on, wait, turn off, wait, and do that so that I get the flash twice. This other one, same thing, it's just I go through it 3 cycles. And then this down here really doesn't matter for what I'm doing. So that's the code, and you saw the output there, the result of it. Now I can come over here, I can press the button, and I can get my 3 flashes when I pull down this line, or I can, again, disconnect that, connect this other line, my P41, to my button pull down, and press that, and I'll get my 1 flash, 2 flash. Now I'm still confused why this block is here that says shadow vectors. So maybe there's something else I need to do to enable these at 7EE0 instead of having to go right down at the 0-100 range. So if any of you know what am I missing to make that work, or is there something, I guess, what am I missing there if I'm missing something? But I can't imagine this block is in here for absolutely no reason. It's got to be there for a purpose, and I just don't quite yet know what that purpose is. And maybe it depends on a slightly different hardware configuration than what I have, or something like that, or something in the ROM monitor that I'm not leveraging. You know, if I was, maybe there's a command or something, it uses that. But this is just a quick video, a quick 20-minute video. I just wanted to supplement the blog post, and hopefully this is helpful to anybody that grabs this board, isn't using an external flash, and wants to have their own user interrupts for whatever purpose. You know, in this case, a button, or maybe you're going to tie a versatile interface adapter to this, or you're going to do something else and you need an interrupt capability. This will let you do that without having your code running off of an external flash with the upper F1000 ranges that you fill in those interrupt service routines.